Okay, here goes. The first thing that's mentioned in our title for section 4.2 is counting. And you're probably thinking, well, how hard could this possibly be? I already know how to count. That's true, and it's not quite true. The counting that we're going to do here may be a little more involved than some of the other counting that you've done in the past. Let's take a look at the type of thing that we're going to be working on. Mary has the following clothes in her closet. For shirt, she has a red one and an orange one. For pants, she has white, black, and gray. This is it. This is all Mary has. And with that in her closet, how many different outfits can she make? Well, one way to go about this is to just start listing them out. So let's see, she could do the red shirt with the white pants, the red shirt with the black pants, and the red shirt with the gray pants. And that's every way she could possibly put together an outfit with the red shirt. That's it. Now we'll move on to the orange shirt. She can do the orange shirt with the white pants, the orange shirt with the black pants, and the orange shirt with the gray pants. And that's every possible way that she could do the orange shirt. So that's it. We've exhausted all the options. How many different outfits can she make? 6. That's them right there. So counting is going to be something that we're going to look at from this perspective. Like, how many different possible ways could something happen? That's what we're going to mean when we say counting. This might be fine with Mary having only 2 colors for shirts and 3 colors for pants, but what if she had 7 different shirt colors and 5 different pant colors? So what if her shirt colors were, red, orange, yellow, green, blue, indigo, and violet? And then her pant colors were red, orange, yellow, green, and blue. And now we start listing these out. And we'll go with the red shirt. So the red shirt could go with the red pants. The red shirt could go with the orange. Oh, wait a minute, this is ridiculous. I don't want to list all these out. Let's think about this for a minute. In the last problem we were working on, what Mary had was 2 choices for shirts and 3 choices for pants. How many total outfits did we come up with for Mary in that last example? Thank you, Ashley. We came up with 6. So with 2 choices for shirts and 3 choices for pants, we came up with 6 total outfits. What's a shortcut? It's exactly what you think it will be. What do we do to figure out how many outfits there will be without necessarily have to list them all out? What are we going to do? What's our shortcut? If we know there's 2 and we know there's 3, how do we get to 6? Multiply. That's exactly right, Kevin. Our shortcut is to multiply. So backing up just a minute, if she has 7 different shirt colors and 5 different pant colors, we don't have to list them out. Instead of listing them all out, we can just say, well, 7 times 5, that's going to be 35 total outfits. What we've just done there is develop what's known as the fundamental principle of counting. When we have a certain number of options for each piece of a problem, what we're going to do in order to find the total number is we're going to find the number of choices for each stage in the problem and then multiply the number of choices together. This is the fundamental principle of counting. Find the number of choices for each stage, multiply those choices together. For example, a code for a garage door consists of 4 digits. How many of these codes are possible? You don't necessarily have to set up a problem like this way, but I always do. I find it really helpful to say, okay, wait, there are 4 digits in this code. So what I'm going to do is I'm going to say, okay, here's the first digit, second digit, third digit, fourth digit. Those are the 4 digits in this code. And what I want to do is figure out the number of choices for each stage in the problem. What I mean by that is when I go here for this first digit in the code, how many numbers are possible? How many things are possible to go in this spot right here? The first digit in the code, how many things are possible? How many different digits could there be as that very first one in the code? And this could be for a PIN number for an ATM is a perfect example of this with 4 digits. So how many different possible numbers are there for that first space? Yeah, very good, Kevin. A lot of times students will say 9 because they're thinking 1 through 9, but don't forget about the fact that there is also a 0 that's possible. So Kevin's exactly right. There are 10 possible digits for that first space. Well, there are also going to be 10 possibilities for the next one, 10 possibilities for the next one, and 10 possibilities for the next one. If we want the total number of possibilities, we find a number for each stage and then multiply those together. And here we'll have 10 times 10 times 10 times 10, or 10,000. So there are 10,000 different possible codes with 4 digits. If you're thinking, boy, that sounds like an awfully big number. Well, I don't know. If we think about the possibilities here, we could have 0001, 0002, and we keep going till we get to 9,999. But higher than 10,000, well, don't forget, we could have 0000 at the beginning. And so that's sure enough, there are 10,000 different codes could be made with 4 digits. So your ATM card has 10,000 different possible codes that, uh, that could be with it. Find a number of choices for each stage in the problem and multiply them together. That's the fundamental principle of counting. I'm going to let you try one. A license plate consists of one number, 2 letters, and 1 number. How many of these license plates are possible? So we have a really small population putting together license plates. And our license plate is a number followed by 2 letters followed by a number. Again, you don't have to do this, but I kind of like to. A number followed by 2 letters followed by a number. Sort of line it out. And now what we want to do is find the number of choices for each stage, multiply those together. I'm going to set up a poll for this, and you tell me how many license plates are possible. So using this configuration, how many different license plates would be possible? We definitely don't want to do this by listing them out. We want to use the fundamental principle of counting to answer this one. How many choices for each stage in the problem, and then multiply those together. Oh, one thing, there are 26 letters in the alphabet. That's an important part of this. So in case you weren't sure how many letters there are in the alphabet, there are 26. We'll go another 20 seconds on this, and then we'll talk about it. If you need more time, let me know. handful of polls today, but a lot of times I'll be just sort of asking questions to sort of make sure that you're with me on the concepts that we're talking about. All right, let's see where we are on this one. Okay, not unanimous, but close. Let's go take a look here. So let's see. We're using the fundamental principle of counting to find out how many license plates are possible. Well, how many numbers are possible in that first space? Well, there's 10 possible numbers. Same thing that we saw in the last one. Now with the letters, there are 26 letters in the alphabet. Any one of them could go here, so there's 26 possibilities. Also 26 possibilities here, and also 10 possibilities here. We found the number for each stage. Then we're going to multiply those together and have 10 times 26 times 26 times 10, 67,600. So with this configuration, we'd have 67,600 potential license plates. If you're thinking with 4 characters on there, you'd have 67,000. That seems like a lot of license plates. Well, if we wanted to start listing them, we could go 0AA0, 0AA1, 0AA2. Okay, this is going to be exhausting. And I'll take your word for it that they're going to be 67,600. A lot of times today, you're going to see answers that are pretty big numbers because, as it turns out, when we do when we use the fundamental principle of counting and look at how many possibilities are for each space, and then we start multiplying those together, we often wind up with pretty large numbers as our answer. Same idea, but there's one little change here. A license plate is one number, 2 letters, and 1 number. So that's the same thing as we saw before. Number, 2 letters, and a number. That's the same thing we saw before. Number, 2 letters, and a number. How many of these license plates are possible? And here's the new part of this one. If repetition is not allowed. So that's the new part here. If repetition is not allowed. What that means is, once I've used a number, I can't use it again. Once I've used a letter, I can't use it again. So with that in mind, let's think this through. Now, it might sound really complicated at first, but honestly, it doesn't turn out to be too bad. So I've got 10 numbers I can pick from for this space, and I've got 26 letters I can pick from for here. It's when I get to this letter, now I have to really think this through for a minute. Once I've used a letter, I can't use it again. I don't know what letter I used right here, but I know I used one of them. One of them is off the table. So how many letters are there remaining for me to use for this spot? How many do I have to pick from? Don't overthink it. It's exactly where your instinct is taking you. Excellent, Ashley. 25. At 26, I used one, so I've got 25 remaining. Using that same logic, how many numbers are possible for this space right here? I don't have all 10 anymore. I have 9. Excellent, Ashley. Very good. Very good. Now I've found the number of choices for each space. We'll multiply those together. We'll have 10 times 26 times 25 times 9, 58,500. So using this configuration, I have 58,500 license plates that I could create. It's less than on the last page, and that makes sense because now I don't have 0AA0 anymore. My first license plate I would make would be 0AB1 because I can't do any repetitions. And so I'm going to have less than I would if I'm allowed to have repetitions. Fundamental principle of counting is find the number of choices for each stage in the problem and multiply those together. Are there any questions about what we've talked about so far? All right. Up next is the idea of factorials. Let's see, 5 horses are in a race. In how many different ways can they finish? Well, there's 5 horses in this race, so I'm going to have first place, second place, third place, fourth place, fifth place. And so the 5 horses are out there running around the track, and At this point, how many of them could possibly finish in first place? How many horses could finish in first place? Oh, let me make sure I phrase this correctly before I have y'all answer it. Um, how many different possibilities are there for the horse that comes in first? That's what I want to say here. Perfect, Ashley. Kevin, yes, I have 5 possibilities for the horse that comes in first. Okay, now one of the horses has crossed the finish line. How many possibilities are there for the horse that comes in second? Perfect, Ashley and Kevin. I think you're probably right there with her. There are 4 horses that could come in second, and then they've both crossed the finish line. How many possibilities for the horse that's going to come in third? Excellent, Ashley. And I think you see where this is going. And then there's 2 horses that could come in fourth, and then there's 1 horse left out there on the track. There's only 1 possibility for finishing last. And so, how many different ways can they finish? We've put together the fundamental principle of counting here. We're going to multiply these together. 5 times 4 times 3 times 2 times 1 is 120 different ways that they could finish. And that's great. The thing is, what if there are 9 horses or 10 horses or 11 horses, and now I've got to do 11 times 10 times 9 times 8 times 7 times 6 times, there's got to be a better way. Sure enough, there is. There's a shortcut way to write 5 times 4 times 3 times 2 times 1. And what that shortcut way of writing that is this. It doesn't mean 5, a very excited 5. No, no. What that means is 5 factorial. That exclamation point that you probably have a button somewhere on your calculator that is either an exclamation point or X with an exclamation point is a factorial symbol. And what that factorial symbol does is, starting at that number, we're going to multiply by every number there is all the way down to 1. That's what the factorial symbol represents. So if we have 7 factorial, that's going to be 7 times 6 times 5 times 4 times 3. Sorry. Times 2 times 1. That's what that factorial symbol means, is we're multiplying, starting at this number, we're multiplying by every number all the way down to 1. So that's what the factorial symbol means. One thing I do want to say about the factorial symbol, it feels a little strange. You can read the description of this in your book if you want to. It's a little bit complex. If we run across 0 factorial, we treat that as having a value of 1. And you can see the description of why that's true in the book. Because it's a little complex, I'd rather stay away from it in class. But if we come across 0 factorial, we treat it as a 1. Okay, permutations. Permutations are arrangements of objects in which order matters. Right now you're thinking, well, I don't know what order matters means, so how do I know if I'm dealing with a permutation? I'm going to let you stay kind of there for just a little bit. We're going to establish how we handle permutations, and then we'll see plenty of examples of cases in which order matters. When we have a permutation, an arrangement of objects in which order matters, we have a formula for dealing with that and solving that, figuring out how many there would possibly be. You can see the factorial symbol right there in the formula. That's an n and r, and it's n factorial over n minus r factorial. What n and r here? N is the total number of objects. And R is the number that we care about in this particular problem. I'm going to say the number being used. And that'll make more sense as we get to examples. But it's the total number is N. The number we care about in this particular problem, that's what R is. And this is our formula for permutation. I said we'd see the types of problems that are permutations. If I'm arranging books on a shelf, for example, and I've got a history book and an English book and a math book. Well, if I rearrange those so that now it's English and then history and then math, the bookshelf would look different. This is an example of when order matters. If I change the order and what I have is something different, then order matters, and that's what points me towards permutation. Once I know I have a permutation, then I know this is the formula I'm going to use to find out how many possible ways this could be done. Let's look at an example. 5 horses are in a race. In how many different ways can they finish first, second, and third? If you're thinking, couldn't I use the fundamental principle of counting here? Yes, you could. But I actually think you're going to like using permutations better, and so that's how we're going to approach this problem. So I have 5 horses in a race, but all I care about here is first, second, and third. What this tells me here is that when I go to use this formula for permutations to find how many different ways this could possibly happen, the total number of horses in this race is 5. And the number I care about, the number in use in this particular problem, is just going to be 3. So what we're going to have here is 5p3. Formally, we would say this is a permutation of 5 things taken 3 at a time. I'm not going to ask you to say that formally, but that's how we'd say it formally, is if we were looking at it and we saw this, what that means is we're looking for the permutations of 5 things taken 3 at a time. Because what we're looking at here is I have 5 horses, and I want to know how many different ways could they finish first, second, and third. I care about 3 places, not all 5. Going back to the idea that order matters, if we're finishing in a race, order definitely matters. And once we know that order matters, we know we have a permutation. We know we're going to use this formula. Now let's take a look at how that formula plays out. So let's see here. I've got 5 is N, 3 is R. With that in mind, I'll plug in. And what I get here is this. I'll have 5 factorial over 5 minus 3 factorial. And so that's 5 factorial over, go ahead and subtract. 5 minus 3 will be 2 factorial. So I've got 5 factorial over 2 factorial. Well, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. 2 factorial is 2 times 1, which is 2. And I can divide and find out that there are 60 ways that these horses could finish first, second, and third. I'm going to back up a little bit here to this place because there's another way that I really like to finish these. 5 factorial, we know what that means. That means 5 times 4 times 3 times 2 times 1. If you're thinking, why'd you write it that way? Well, because I'm going to get something to cancel here in the denominator. I know 5 factorial is 5, 4, 3, 2, 1. I'm going to write the 2 times 1 this way because I already have a 2 factorial in the denominator. And if I stop at 2 factorial, then when I write my 2 factorial in the denominator, these will cancel. And now it's just 5 times 4 times 3. 5 times 4 is 20 times 3. Sure enough, I get the same answer that I got the other way. I was able to cancel that denominator and make it a little more efficient. Okay, I've kind of held out on you a little bit, I have to admit. On your calculator, depending on what calculator you have, somewhere is an NPR button. You have a button that can do permutations. Depending on your calculator and the syntax, and we can talk about that if you need to, but if you put in the 5 and then hit your NPR button and 3, and then either equal or enter, depending on which calculator you have, that should take you straight to 60. Doing this by hand, using the formula and doing this by hand, I don't think is a hard process. I don't think it's a time-consuming process. So if you're doing it by hand, I don't see that as a huge disadvantage at all. But most of you will probably prefer to use your permutation button. You're not cheating. It's totally fine. You have the button. You learned how to use the button. There's absolutely nothing wrong with using the permutation button. As we go through these permutation problems, feel free to either solve them by hand or by using the permutation button. Permutations happen when order matters. We have a formula for working with those, and you can either solve it by hand or by using the button. Any questions on this before I have you try one? Okay. Sophie has 8 unicorn figurines. She's going to arrange 5 of them in a line on her dresser. How many different ways can this be done? Before you start, it's obvious this one's a permutation because we're given a pretty big hint. But I want you to be able to recognize when we have a permutation. Notice, she's going to arrange these on her dresser, which means if she puts the unicorns this way, A, B, C, D, E, they're going to look different than E, A, B, D, C. Because it will look different, there's a change. If the order changes, something's different about this. So order matters, and that's how we know we have a permutation. Okay. I'll step aside for a minute, set up a poll for this, and let you solve it. How many different ways can she arrange 5 of those 8 unicorn figurines on her dresser? We'll go another 30 seconds, and then we'll talk about it. You let me know if you need more time. See where we are on this one? Unanimous is usually a good sign. Okay, so let's take a look. We've decided that we have a permutation, which means The formula we would use here is n factorial over n minus r factorial. In this particular case, we have 8 total items and 5 are going to get put on the dresser. So we have 8 total objects and 5 that are in use, 5 that we care about in this particular problem. So we have a permutation of 8 things taken 5 at a time. That's what we're working with here in this one. If you're comfortable and happy using the button on your calculator, it's perfectly fine for you to do that. I'm going to work this one out by hand just so you see what's happening inside your calculator and so that you know how to do it just in case anything goes haywire with your calculator during a homework or a quiz or an exam. So we'll have 8 factorial over 8 minus 5 factorial. Doing what's in the parentheses first, we'll subtract and have 3 factorial on the bottom. Now what I'm going to do is I'm going to rewrite that 8 factorial. I know it means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And I'm going to write that. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. The 3 times 2 times 1 I wrote as 3 factorial because I have 3 factorial in the denominator and I want those to cancel. Now all I have left is 8, 7, 6, 5, 4. 8 times 7 times 6 times 5 times 4 is 6,720. And that's the number of ways that Sophie could arrange 5 of her 8 unicorns on a line, in a line on her dresser. Poll went great, but I want to give you a chance to ask any questions that you might have about that one before we look at one more permutation question. Okay. You might see a permutation question that just goes straight at it and says, simplify 6p2. That's a permutation of 6 things taken 2 at a time. So we're going straight from here into our formula where this is just 6p2, and we're just going to solve it. If you want to use the button on your calculator, that's totally fine. Or we've got 6 factorial over 6 minus 2 factorial. And that's 6 factorial over 4 factorial. I'm going to rewrite my numerator. 6 times 5 times 4, 3, 2, 1. Got a 4 factorial in the denominator. Those cancel. 6 times 5 is just 30. So if we want to simplify 6p2, we end up with 30. If I had a permutation of 6 things taken 2 at a time, there'd be 30 different ways that those things could be ordered or arranged. If you have any questions on that, please let me know. Otherwise, we're going to move on to combinations. That's our third topic for today. All right. Combinations are a collection of objects in which order doesn't matter. Gotten pretty used to the idea that order matters, and now we're going to say order doesn't matter. Well, when in the world would order not matter? And an example of that might be, let's say there are 20 students in a classroom and 4 of them are going to be chosen to stay after class and clean the room. It doesn't really matter who's chosen first, second, third, or fourth. You're either chosen or you're not. You're either one of the students who's cleaning the room or you're not. The order that you're chosen in doesn't matter. And when order doesn't matter, that's when we have a combination. Combination has a formula that is n factorial over r factorial outside of our parentheses of n minus r factorial. So it's almost the same as the formula for a permutation. The only thing that's different here is this r factorial out front. What that does is that prevents us from counting things twice. With a permutation, AB and BA are seen as different from each other. As far as a combination is concerned, these are the same. And so we wouldn't want to count that twice with a combination, and dividing by this number right here is what eliminates those duplicates for us. So that's our formula for a combination. And we use that when order doesn't matter. And an R mean the exact same thing that they used to. Let's look at one of these. A student can pick 3 of 5 essay questions to answer. How many different ways can the student pick the questions? Notice, the student's not putting them in a certain order. They're just picking. And each question is either going to be picked or it's not. It doesn't matter which one gets picked first or second or third. The question's either picked or it's not. And so that's what tells us that order doesn't matter, and we have a combination. Since we have a combination, the formula we're going to use here looks like this. And in this particular case, what I have is 5 total essay questions, and 3 are going to get picked. Or, as you might expect, a combination of 5 things taken 3 at a time. There's also another shorthand way to say this with a combination is this thing right here. We might say 5 choose 3. It's a nice little shorthand way to say a combination of 5 things taken 3 at a time is 5 choose 3. If you found that NPR button on your calculator, it's likely that very close to it is an NCR button on your calculator. And here we put in the 5. NCR tells the calculator we want a combination, 3, and then either enter or equals. And just like before, it's perfectly fine for you to use this button. If you don't have it, you're going to see that it's not really arduous to do this by hand. But if you do have a combination button on your calculator and you want to use it, by all means, go right ahead. I'm going to do this one by hand. And we'll have, let's see, that's 5 factorial over 3 factorial, 5 minus 3 factorial. First thing we'll do is subtract inside those parentheses. And have 2 factorial. If you're doing this by hand, there's a little danger here I want to make sure to keep you away from. And there's a little danger of wanting to multiply these 2 together and call that 6 factorial. Don't do that. Keep in mind what 6 factorial means is 6 times 5 times 4. Well, if we look at these numbers, there's no 6 anywhere, there's no 5 anywhere, there's no 4 anywhere. We definitely don't want to multiply those together. We're going to leave them as they are. I'm going to do the same thing I did before where I rewrite my numerator in a way that helps me cancel something out. And as I look at this, this is the bigger of the factorials on the bottom. So that's the one I'm going to sort of zero in on. I'm going to rewrite my numerator here as 5 times 4 times 3 factorial. On the bottom, I've got this 3 factorial, so I'm keeping that because it's going to cancel. And then I'll also have the other one, the 2 times 1, I'll go ahead and write that out. And now at this point, what happens is those 3 factorials cancel, and I have 5 times 4 on the top, which is 20, and I have 2 times 1 on the bottom, which is 2. I'll divide those and end up with an answer of 10. So if a student can pick 3 of 5 essay questions to answer, how many different ways can they pick the questions? 10 different ways. Again, if you like your combination button, feel free to use it. I'm back up again. I tend to want to cancel as much as I possibly can before I multiply. Maybe you're the same, maybe you're not. I found that over time, most students like to get here go ahead and multiply these to get 20, multiply those to get 2, and then divide. And that's absolutely fine. If you really like canceling, then you might say, well, dividing by 1 doesn't do anything, and 2 will go into 4 twice, and now all I have left to do here is multiply 5 times 2, and I'll get my 10. So I kind of like to cancel as much as possible. It's kind of fun, and then see what's left and multiply it. If you'd rather multiply 5 times 4, multiply 2 times 1 and divide, that's fine. And of course, if you'd rather use a combination button, that's totally fine too. Are there any questions about this combination problem before I have you try one of these? Okay, here goes. Simplify a combination of 6 things taken 2 at a time. Just straightforward, using the formula, combination of 6 things taken 2 at a time. I'll set up a poll for this one. You can use the formula and do this by hand, or you can use your combination button. I think it's great to practice getting used to the syntax, the way to enter the numbers correctly for the combinations and permutations if you're using those buttons on your calculator. If that's the way you're going to go, you want to make sure that you're comfortable with the process of using those buttons. We'll go another 15 seconds and then talk about this one. If you want more time, let me know. See where we are on this one. Okay, not unanimous this time. We'll talk through this one, and please let me know if you have questions. So here we have a combination of 6 things taken 2 at a time. So we're going to use the formula for combinations. N is going to be 6, R is going to be 2. Let's plug this in and see what happens. So we have 6 choose 2, and that'll be 6 factorial over 2 factorial, 6 minus 2 factorial. So that's 6 factorial over 2 factorial, 4 factorial. We're not going to multiply those together on the bottom. Instead, we'll have 6 factorial on the top. We're going to rewrite that as 6 times 5 times 4 times 3 times 2 times 1. Reason we stop at 4 factorial is I have this 4 factorial on the bottom that'll cancel. That 2 factorial, I'll just write it out as 2 times 1. And now these cancel, and you could do 6 times 5 is 30, 2 on the bottom, divide and get 15. Or if you really like canceling stuff, you'd say dividing by 1 doesn't do anything. 2 will go into 6 3 times. So 3 times 5 is 15. Either way, combination button or by hand, we end up with 15. A combination of 6 things taken 2 at a time can be collected together in 15 different ways. Any questions on that before I have you do another one? All right. Malcolm is going on a trip and will choose 4 of his 11 t-shirts to bring. How many different ways can he choose the shirts? One thing I want you to notice here right away out of the gate is he's choosing the shirts. They're not being put in any certain order. He's not deciding what he's going to wear on Sunday, Monday, Tuesday, Wednesday. This is strictly just they're either going in the suitcase or they're not. They're being chosen or they're not. So order doesn't matter, which means we have a combination. With that in mind, I'm going to let you try this one. How many different ways can he choose 4 of 11 shirts to bring on vacation? And as you're working on this one, and I set up the poll for it, I'll let you know, this is the top of the mountain today. This is probably as challenging as things get for us in this section. So how many different ways can Malcolm choose 4 of his 11 shirts to bring on his trip? Definitely the type of question you can expect to see on a homework, on a quiz, on an exam. We'll go another 30 seconds and then we'll talk about it. If you want more time, just let me know. All right, let's take a look at this one. Fantastic, unanimous. When that happens on the toughest question of the day, that's really good news. All right, so we know we have a combination. So the formula we're going to use here is this one. Oops. And in this case, he has 11 total shirts, so that's going to be N. And he's choosing 4 of them to take with him, so that's going to be R. So this is 11 choose 4, or a combination of 11 things taken 4 at a time, depending on how formal you want to be. As we plug in, we'll have 11 factorial over 4 factorial, 11 minus 4 factorial. And that's 11 factorial over 4 factorial, 7 factorial. Okay, now I'm going to rewrite that. There it is. All right, 11 factorial over 4 factorial, 7 factorial. I'm going to rewrite that 11 factorial as 11 times 10 times 9 times 8 times 7654321. And I stop there because I have this 7 factorial on the bottom that'll cancel. The 4 factorial I'm going to write out as 4 times 3 times 2 times 1. These are going to cancel. And now at this point, I have choices. I can multiply everything on the top, 11 times 10 times 9 times 8, and have 7,920. And multiply 4 times 3 times 2 times 1 on the bottom, and have 24. And then I can divide those. 7,920 divided by 24, and I end up with 330. That was our unanimous answer, so I feel really good about that 330. But just because I like doing it, if we were going to keep canceling stuff, dividing by 1 doesn't change anything. And then 4 times 2 on the bottom, that's 8. That'll get rid of this 8. And then 3, we're going to 9 3 times. And so what I'm left with here really is just 11 times 10 times 3. Well, 11 times 10 would be 110 times 3 would be 330. And there you go. Same answer as what we got in either of the other methods. Without all that canceling, I know there's not very many students that really like all that canceling, but I like showing it anyway. And then you're welcome to use your NCR button to solve 11C, 11 choose 4. Poll went great. If you have questions, let me know. I just have one more thing to talk about today, and that's some helpful hints. I do not think you're going to have difficulty with the calculations in this section. One thing that I do want to mention is do not forget about the fundamental principle of counting. What happens sometimes is we spend so much time on permutations and combinations that it's really easy to forget about find the number of choices for each space and multiply those together. You will see some problems that find the number of choices for each space and multiply those together is how you solve them. And don't try to force permutation or combination onto those, because that's not what they are. Sometimes it's, I have license plates, I have garage codes, I have, these things. Find the number of choices for each space, multiply them together, and that's all there is to it. The hard thing I think that will come up in this section is trying to decide, is this a permutation or a combination? When that happens, what I want you to do is look for keywords that are in there. Words like arrange or order point us towards permutation. Those are words that let us know order matters. If I'm going to arrange something, the order matters. Or if we're coming in first, second, and third in a race, or if I'm going to line things up on a dresser or books on a shelf, the order matters, because if I change the order, it looks different. If instead I see words in there like select, pick, or choose, Malcolm was going to choose shirts to take on his trip. A student was going to pick 3 of 5 essay questions. These words give me an indication that, you know what, this isn't about putting things in a certain order or arranging them in a certain way. This is just choose them or don't choose them. There is no order involved, so order doesn't matter with those words. Now, not every problem you see will have these necessarily, or these keywords necessarily in there. But what you can do is, if the problem you've been given doesn't have any of those keywords in it, see if you could replace the verb in there with one of these words. And if arrange or order makes sense, then your situation is likely a permutation. If changing the verb that's in there to choose or pick or select makes sense, then it's strong likelihood that the situation you're dealing with is a combination. But I do think that's probably going to be the most challenging piece of this is it a permutation or combination? More so than the actual calculations that are involved.